we need to divide out that factor to be able to do the rest of it. So what we're going to do is we're going to take those coefficients that we had, just like we did yesterday, these guys here, where we're going to have our 3 from the x cubed, our 7 from the x squared, our minus 12 from the x, and our minus 28. That's meant to be a 28. There we go. And we're going to set up our synthetic division here. What number is going to go in the little box? Almost. -2. I know it's early. So that's when we're looking at our factor here, and we need to get it back into a root. So we need to know when x plus 2 equals 0. That's how we know that we need -2. So we have to set that factor equal to 0. We need to find that root. The root is what's going in the box at -2. 1m. So that's why I left it cracked, because I figured there's going to be a bunch, because there's a whole lot of people out running. Yep. Sweet. Let's. All right. So this is how we set it up. This is where we start. Now we're doing that same process where we're going to drop the first term all the way down to the bottom. The 3 hits. Then we're going to take our 3 times our -2 and put it under. We're going to have a -6. Then we add these together. 7 plus -6 gives us a 1. We take our 1 times our -2 and put it under. So we're going to have a -2 here. And then again, we add these pieces together. -12 plus -2. Absolutely right, -14. Which means when I multiply together my -14 and my -2, we're going to get ourselves a positive 28. Which gives us a remainder of 0, which means for sure x plus 2 is a factor, and we can keep going because we are awesome and we've got the skills to back this up. Say it again. You don't have to, but I do recommend it just because looking at it like that is hard to see. But I mean, like, you don't necessarily have to, because we're just going to take them back away for a second. But yeah, this is going to go with our x squared. This guy's going to go with our x, and this guy's are just the number. So this is giving us the quadratic. That's our 3x squared plus 1x minus 14. I don't like the way that arrow looks. It looks weird. A lot of times we're more comfortable factoring from here. You technically can do it. Oh, hard crash. Give me that back. Hey, we're back. You technically can do the factoring from here, but it's like awkward and uncomfortable. I recommend putting it here. If you can go from here, more power to you, but honestly, this is usually easier to work with. Because it's more familiar. We've seen this. We've done this. We've been through this a gabillion times. This is where we're going to factor it. We're going to use our x. Probably going to use the box. You don't have to use the box. You can do it in quite a large number of ways. There are so many options when it comes to factoring. It's where we take our a times c at the top. B goes at the bottom. So we're going to have our 3 times -14. So I have to think that one for a second. We've got -42. And a positive 1 at the bottom. So we're looking to see if we can find a pair of numbers that multiplies to make -42 and adds to make 1. When in doubt, make yourself a list of things that multiply to the top. Since the top number is negative, we're looking at their differences. So maybe it's 1 and 42. It could be 2 and 21. We had our 3 and 14. Yeah, I don't think it divided by 4. I'm just gonna finish out the list just so we can see it. 4 doesn't go in evenly. 5 doesn't go in evenly. 6 and 7. So since the top number is negative, we're looking at our differences, and the only pair here that have a difference of 1 is the 6 and 7. Which of those needs to be negative for this to add up to be a positive 1? The 6. So if it's not something we spot right away, that's a way to kind of work through it. If we cannot spot the pair of numbers that multiplies, make a list of your factors, figure out if we're looking for the sum or the difference, and just plow through it that way. So what we have here is we're getting our 3x squared from our equation and our minus 14 from our equation. And then we have our minus 6x and our 7x. Because what the x frame does is it splits this guy back into its uncombined like terms. And then we're pulling our factors in columns and rows. What do we get as factors here? Yep, we get a 3x. What else do we get? Yep, we get a 2. Does that 2 need something else to go with it? I just said we'll have an x here. What are we missing from this column here? It's not going to be a regular 2. It's going to be a negative 2. Last box. Or last spot over here. What's shared between 7 and 14? 7. Oop, there we go. So our factored form of this quadratic is our x minus 2 and our 3x plus 7. So if we want this to be our g of x in its factored form, we're going to take those two pieces from our quadratic, and we've also got to put back in the guy we divided out at the very, very beginning. So we've got our x plus 2. So that's our factored form of our polynomial, and if all we were asked for was our factored form, that would be where we stopped. Well, we weren't asked just for factored form, we were asked for our roots. So we need to find them. We're almost done with it, though. So our roots are going to be when we set each factor equal to 0. So we already have one of them, our x plus 2, we did up here. So one of our roots is that x equals minus 2. One of them, we might not have to actually even write anything for, x minus 2 equals 0. We're going to get a root at positive 2. And the last piece, we are probably going to need to write it out because it's kind of gross. It's going to wind up fractiony. Our 3x plus 7 equal to 0. Subtract 7 from both sides. 3x equals minus 7, which means our root, when we divide both sides by 3, we're going to have negative 7/3, which is gross, but fine, I guess. We can do it, it's just unpleasant. These are the answers we're looking for. We were asked for roots. We got to make sure we get all the way down to our root solution, zeros, x-intercepts, those guys. When I said find all roots, that's those. There's a whole lot of work to get to those roots. Questions on this one? So, that is the exact same SAT question as we had yesterday. We're just going to skip it then. I'm not going to come up with another one. So we're just going to move on. We're not going to do an SAT talk through today because it was the exact same question as yesterday. Whoopsies. So what we're going to do is we're going to work through our last section in this chapter. And honestly, we're probably going to get through everything we need to, like everything we need on it today so we can finish out the chapter today, but we'll like talk through stuff on Monday as well. I have this printed for you because the first couple of slides on this are almost entirely words. So I'm going to pass these out, and then I'll walk you through how to fill this in. On review from the last chapter, we had those random questions that we didn't know how to answer. This is us going through that now. Those questions were direct answer. So, we're going to work with something that's called the fundamental theorem of algebra. You don't need to know the name, but it's there. And what this is telling us is that for any polynomial, all polynomials in the entire existence of the universe have a couple of things that are true about them. And what it is that our maximum number of roots that we could ever get on a polynomial is going to be 100% exactly the same as the degree of the polynomial. The maximum number of roots is the degree. So on a quadratic, on an x squared, we will only get 2 roots at the very, very most. On a cubic function with a power of 3, we will only get 3 roots. That is the very, very most we can get. On a 4th degree polynomial, the most number of roots we can get is 4. So the most roots we can have is our degree, is that power. The minimum number of roots depends on one thing. Depends on whether it's even or whether it's odd. Because if we think about our even polynomials, I'm just going to draw some things down here. I know you don't have any space between here. So if we think about our even polynomials, that's when we have powers like 2 or 4 or 6. 2 is when we know like parabolas. Maybe it could be upside down and like have a couple of wiggles. And yes, I could wind up with, in this case over here, 4 real roots if it goes through my axis like this. But even degreed polynomials do not have to cross an axis. They can have no real solutions. We had that with our quadratics back in that chapter. So if we were looking at even polynomials, evens don't need to have roots. So the minimum for evens is 0. They do not have to cross the x-axis. It could look like this. Even whether they're above or below, it doesn't matter. They do not have to cross the x-axis. Odd degreed functions, let's get odds. No matter what degree we're thinking, so odds would be things that are power of 1. We could have a power of 3. I could have more than that. I could do 1, 2, 3, 4, 5. No matter what happens, no matter where I put my x-axis, I'm going to have to cross it somewhere. Since my arrows go in opposite directions, because odd ducks go to the disco, alternate directions. Since we have those opposite arrows, it has to cross at some point, because it's going from negative infinity to positive infinity. It's got to cross the x-axis. So odd degreed functions must have at least 1 real root. Evens do not have to have any. That's when we'd have our no real solutions. Odds have to have at least 1. They have to. And then this last statement is talking about the kinds of roots we can have. So when we have roots that are on our axis, that's when we call our real roots. Those are those numbers. Those are those roots we've been finding. The one we just did in the bell work was one that looks like this. We found 3 real roots. 1, 2, 3. So the number of real roots we have and the number of, if we don't have real ones, they are imaginary will combine together to get the degree. So if we only have one real solution on a cubic polynomial, we're going to have two imaginary roots. If I have two real roots on a quadratic, on an x squared, I don't have any imaginaries because it can only have two. So the number of real roots and the number of imaginary roots combine to make the degree. And the most number of roots we can have is the degree. So that's one of those things it's like the reason why algebra exists is to find these roots, these solutions for polynomials. That's where it's all kind of born from. So the next two statements on this little quarter sheet printout thing I had for you are where we're going to practice this. We're going to look at these two polynomials that I gave you, and we're going to see if we can figure out how many real roots it would have, how many imaginary roots it would have, how many it's going to have, all that jazz. So we know the real roots plus the imaginary roots has to equal the degree. So we've got a polynomial here. It's a big one. I don't want to have to write it down. What is the degree on this polynomial? What is our degree? That's my first question. It's the biggest exponent. So our degree is 3. Which means, what is the absolute most number of roots we can get for this polynomial? 3. The absolute maximum. I am never going to have 4 roots on this guy. I will never have 6 roots on this guy. I will have exactly 3 roots. So is this even or odd? It's an odd function, which means I have arrows going in opposite directions, which means it has to have at least how many real roots? 1 real root. Since it's an odd function, it has to have 1. And the last one is just saying, all right, if we have this information, so if I have 3 real roots, we know the number of real roots plus the number of imaginary roots has to equal the degree. That's what the very last statement on the first page said. Over here. Just because if I put it over there, people use it and they put like hand sanitizer on it and they wet my desks. Yeah. And tissues are expensive. So they're telling us if we have 3 real roots, and then we also already said we knew the degree was 3, what would fill in this blank? 3 plus what gives me 3? 0. So if I have 3 real roots, there's going to be no imaginary roots. The number of real roots plus the number of imaginary roots has to equal our degree. I am going to scooch those over just because I have no space to write for the bottom one. So then we're doing the same kind of vibe on the bottom one. Just scooching it over a smidge. On this bottom one, what's our degree? 2. Ooh, chunky marker. There we go. Our degree is 2. It's that biggest exponent. So what is the maximum number of roots this is going to have? 2. What is the absolute minimum it has to have? It doesn't have to have one. Quadratics, we had that happen before when we did that chapter back in last semester. We would get no real roots. We would have just imaginary roots. So it's entirely possible to have no real roots, but only on even functions. So if there are no real roots, so they're telling us right now that if we have no real roots, how many imaginary roots would we need to get? 2. Because our degree was 2, so there have to be 2 imaginary roots. If we have no real roots, that means we must have 2 imaginary roots. Okay? So it's just kind of like super awkwardly worded. It's not a particularly difficult thought process, but it is just weirdly worded and like severely overcomplicating things sometimes. There are not tons of questions like that. Mostly what we use this for is when we're going to start sketching these polynomials. which what we're going to do next is we are going to look at everybody's most favorite thing in the whole wide world, graphs. Sorry. Not sorry. This is the last, big part of this. We're going to work on being able to, graph these significantly close to fully properly. Thank you. I'll put this one over here, and I'll grab the other hand out of it. So we are going to do 3 of these today. And what we're going to start with is we're going to start with figuring out how many roots it has to have, how many roots it might have, and we're going to see if we can find those roots. I'm so good at counting. Almost like I'm a math teacher or something. What? I definitely always count the right number of things for every row. I'm so good at counting. All right. So looking at this polynomial here, I've got one up here for us. It's in factored form. What's our degree? How could we find out the degree on something like this? How many x's are being multiplied together in this factored form? 3 of them. I have x times x times x. So our degree on this one, if I was to fully multiply this out and get it back in a standard form, I would have taken my x times my x times my x. So we'd have a degree of 3. Which means we know that this is a, which one, even or odd? Odd, because 3 is an odd number. Which means we know our arrows are going to go in opposite directions. How about our leading coefficient for this? Is it going to be positive or negative? I'm going to zoom in on the polynomial for us real quick. Our leading coefficient, is it going to be positive or negative? Negative. Because of this guy right here. We've got a minus sign in there. Back up. So we know this is going to be negative. So once we know it's odd and we know it's negative, what's going to happen with our arrows? They're going in opposite, and the right one is going to point which way? Down. So I know somewhere over here we're going to have a down arrow. Somewhere over here we're going to have an up arrow. And I tend to draw them off to the side of the graph like this just so I can use them later and I don't have to necessarily redraw them. My graph's just on the bottom of the page and I physically don't have a below here. Then let's look at our factored form and see if we can figure out where our roots are. Where are our roots? How about for x plus 2? Where's our root going to be? At negative 2. Oh, I need the skinny pen for that one. We'll have x equals negative 2 as a root. What about for this guy, x minus 6? X equals 6. And how about for this guy, x minus 1? X equals 1. That gives us our roots, our zeros, our x-intercepts. So if this is counting by ones on my graph here, because yours is numbered, mine is not, but yours is numbered, we are going to have a root at negative 2. We are going to have a root at positive 1. And we are going to have a root at positive 6. 1, 2, 3, 4, 5, 6. If you want to have more points, we can do kind of plug and chug situation. There's one more thing that it's not super hard to get, and that's actually our y-intercept. To get our y-intercept, just so we can kind of make sure things are doing what we need them to do, we're going to take everything that's not an x up here and multiply it together. So if I take, writing it down, to get my y-intercept, I'm going to take my minus sign from out front. I'm going to take the positive 2 from the first piece. And I'm going to put that in the blue just so we match the root. we're going to take our minus 6 from that green one, just from the factors. I'm just dropping all the x's, just taking all those numbers at the end, and our minus 1. If I multiply minus 2 times minus 6 times minus 1, what is minus 2 times minus 6 times minus 1? What's minus 2 times minus 6? Just this part. 2 times 6? 12. Minus times a minus? This becomes a positive, right? So this is 12 times minus 1. Our y-intercept's going to happen at negative 12, which I know is not actually on our graph, but that lets us know we're going to have a point way down here somewhere. So we can connect up our arrows, going through the dots we have, and kind of getting the vibe of the graph. I'm going to use the second marker for that. So we're going to start at one arrow. We're going to go through all of our points. No loop-de-loops. No trick shots. No banking it. Left to right or right to left. I don't care how you connect it, but no trick shots. No loop-de-loops. And you don't necessarily have to do this y-intercept part, but it does sometimes help when we're looking at stuff. Because if we're looking at our polynomials when they're in standard form, it's going to wind up being that last value, our c value. It's what happens when we take all those constants and multiply them together. So when we're given factored form, to get that y-intercept, we just multiply the numbers that we see. We had ones very much like this in the last chapter where we gave it to us in factored form. But we haven't been working very much with things that were already in factored form in this chapter, have we? We've been doing a bunch of, like, you know, factoring. Oh, snap, I wonder what we're going to do in the next ones. I'm going to give you an equation in standard form. What? And we have to figure out our factored form ourselves. So we're going to have to come through and factor these. So on this one, I only have 3 terms. What is our degree? Let's work our way down the page first. What is our degree? 3. So we know it's going to be odd. We're going to have our arrows going in opposite directions. What's our leading coefficient on this, positive or negative? Positive. It would be the number in front of our x cubed over here. So I know when it comes time to graph it, my right arrow is going to point up, and my left arrow is going to point down. Because we're going in opposite directions, my leading coefficient tells me about the right arrow. If it's positive, it's going up. If it's negative, it's going down. To find our roots, our zeros, our intercepts, we're going to need to do some factoring. What can I do to this thing as a first step when we're factoring? What should we always check for first? What should we check for first? A, G, C, F. Check for GCF. Does this have a GCF? Yes, it does. You're always zombies today. Oh my gosh. This has a GCF. What do all 3 of these pieces have? An X. We can have an X as a GCF. If I take an X out of that polynomial, what we're left with is an X squared minus 2X minus 3. This guy's a quadratic. That's an X and box thing. So we can factor that piece using our X and box. I'm going to move the box down just a little bit, just so I have space. where we take our A and our C. We have a -3 at the top, and our B is -2. What pair of numbers multiplies to make -3 and adds to make -2? What numbers multiply to make 3? One and 3. So if I need it to add to be a -2, which of those needs to be negative? The -3. So when we're filling in the box to be able to, our factoring, we're going to have our x squared from our equation and our -3 from our equation with the -3x and our +1x. So when we pull our factors, we're going to have our x -3 and an x and a 1. So our factored form of this polynomial, we have our obnoxious little line leader, x. And then we have those two factors from the box with our x -3 and our x +1. So where do we have roots on this one, or zeros, or intercepts? What's the root for this guy, x +1? -1. So we're going to have a root at x equals -1. What's our root for this guy? +3. What about this guy? We have an x over here, so we got to include him. What do we do with our factors to figure out what our root is? How do we figure out this was -1? Set it equal to 0. So on this one, set it equals 0. X equals 0 means our root is 0. We can have roots at 0. So we have a root at x equals 0. So when we come over here to our graph stuff, we're going to have a root at -1. We're going to have a root at 0. They're very close together here. And a root at +3. So my arrows are probably a little far apart, but we can get the vibe. We're going to start at one arrow, go up through one root, back down through the other, back up for the third, and to the other arrow. Since we have a root at 0, we do not have a y-intercept term up here. If we had a y-intercept, it would be the very last term that was just the number. This one's a 0 because we have a root there. So our y-intercept would happen exactly at 0. Okay, questions on this one? Sometimes, though, it won't have a GCF like that. Sometimes we're going to give you a factor, and it's going to smush together all the things like we did in the bell work with this. Oh, my gosh, what? Because we have here, given x +1 is a factor, this is our last one here. We are still asked to find our zeros, intercepts, degree, leading coefficient, all that jazz. So what is our degree? 3. For the most part, we are giving you cubics just because they're easier to deal with, which means we know it's going to be an odd function. Our leading coefficient is positive because we have a positive number there. So I know my arrows are going to be in opposite directions, and the right one's going to point up. So my arrows are going to look kind of like this. Then, in order to find our zeros, our roots, our intercepts, we're going to need to do like we did in the bell work, where I divide out that factor so that we can find our roots. So we're going to do a synthetic division here. I need to take my 1x cubed, my -1 from my x squared, my -17, and my -15. And we're going to use our root from this factor up here, the x +1 we're told, which means we have a root at -1. That's the guy we're dividing out. It's also one of our roots. We love that. Saving us a little bit of work. Doing our synthetic division, first term drops all the way to the bottom. 1 times -1 is a -1. We add these two together. -1 plus -1 gives me a -2. -2 times -1 gives me a +2. -17 plus 2 gives me a -15. -15 times -1 gives me a +15. And we get our remainder of 0. What this tells me is we now have a quadratic term that has our x squared minus 2x minus 15. And we still have more to do because I need to be able to graph that thing. I need my factors from this. So I'm going to do the x and the box. I have very little space over here, but that's okay. We're going to take our a times c, our -15, over our b of -2. We need a pair of numbers that multiplies to make 15 and have a difference of 2. I heard it. It was very quiet. It's 5 and 3. Which one needs to be negative for the 2 to be negative? The 5. So putting it through the box, I'm almost out of space, so I'm just going to go straight to the pieces. Our factored form here, we're going to have our x minus 5 and our x plus 3. So what are my other two roots that we have? -3 and +5. So we can get our roots here with our -3, our -1, and our +5. 1, 2, 3, 4, 5. So we're going to connect this up. I'm going to go from one arrow up through a root, down through a root, up through a root. If I had a big enough graph, we could use our y-intercept. Our y-intercept is always going to be this last term here, same as it was for quadratics. I do not have a graph physically that'll fit that number, so I'm not going to be super concerned about it. And that's going to be true for a lot of them, but the y-intercept would be that last term there. We talked about that a little bit in the last chapter. Questions on this one? Okay. This is the last section of this chapter. We're going to keep working with these on Monday. They don't really get worse, but they are awkward, and I went through those kind of fast. So what I have for you guys is the very last homework of the chapter. Aha! We love it. Our chapter test is next Friday, 1 week from today. So I'm going to give you guys the very last homework. We will go through some more of these and practice some of them on Monday. And then after that, we're going to be getting ready for the test that's coming up on Friday. We also have an e-learning day next week. We have a short day here at convocation. There's shorter periods at least, not to go even shorter. So like next week is one of those kind of weird weeks where just there's a bunch of chaos happening. So probably I'll have some bell work. So make sure you turn in your week 5 bell work. Please make sure you do put week 5 on it and your name. I have a shocking number of them that come in with no names. Also, if you ever get the notice in Canvas that you are missing bell works, I still have 1, 2, 3 bell works, 1 homework, and a review from last chapter on the no-name board in the back. So if you've done the work, you might as well claim the points. But that is it for this week. And on Monday, we'll practice a little bit more of these. And then we'll just be getting ready for the test on Friday. And I'm going to put up announcements.